Okay, our job in part 4a is to determine the slope through the points P and Q. So what we're going to do is, you can just do this algebraically, but what's more important is for you to understand the procedure here, what's going on. So what I'm going to do is, when I say the procedure, I mean why are we doing this? I shouldn't really just say procedure, but what's the point of all this? Well, look, let's say we have a function f of x, which gives us out x squared plus 2. And let's say I plug in some value x. Well, then, if I plug in x into x squared plus 2, I get x squared plus 2 back out. So, let's say this is a height of x squared plus 2 right here. Because the actual function, x squared plus 2, maybe looks something, I shouldn't say maybe, but it looks something like that. So what we're going to do is we're going to pick some random x on this curve. Of course, it goes on the other side too. I'm just not going to draw it. So we're going to pick some random x right here, and it has a height value. So it's got a length over this way and a height value up this way. Okay, so clearly the point x squared plus 2 is on the curve x squared plus 2. It's right here. Now what we're going to do is we're going to move over a little bit. Okay, and the distance that we're going to move over, we're going to call it h. You can think about this as calling it delta x if you want to. It's the exact same thing. So this length that we move over is h. So if this was, I don't know, if x was like 3, and I moved over h, this would be 3 plus h. If x was 7, and I moved over h, this would be 7 plus h. So if this is x, then I move over x plus h. Okay. So then x plus h also has a height value associated with it, and it falls on the curve up here. Okay, and its height is x plus h squared plus 2. It's the function evaluated at x plus h. And so what I want to do is I want to find the slope of the line containing those 2 points. So I want to find the slope of this green line. Now, why are we doing this? Well, in a couple sections, we're going to take h, we're going to make it really small. So this distance that we go over right here is barely anything. And what that does is that takes this red point and pushes it towards this blue point. And when the red point and the blue point are super close to one another, we don't get the line for the slope for the secant line, we get the slope for the tangent line. And that's what we're going to be looking for, because the tangent line is important in calculus. We study it because we want what's called an instantaneous rate of change. Okay. So our job here in this problem, since we haven't talked about limits or anything, is just to try to calculate the slope of this green line. So this guy up here has coordinates x plus h squared plus 2, just like I've got up here in the problem. Okay. So again, if you just look at this problem, you're like, well, I can compute that. That's not a problem algebraically. That's great. But this down here, this picture, what's going on, this is what's important. Okay, so don't forget about why we're doing this up here. We're doing it because we want to find these tangent lines. We're going to do that using these secant lines. So to calculate the slope, I'll take the difference in the y values. So let's do the slope over here in yellow. Okay, so the slope is the difference in the y values. So x plus h squared plus 2, that's this y value, minus this y value, which is x squared plus 2. We'll put that in parentheses because we want to subtract the whole thing. Okay, that's over the change in the x. So this top part, this change in the y, is this length right here. Right? It's this height minus this height, and that gives you this length right here. Now we want the change in the x's. Well, the change in the x's is this length right here, which is x plus h minus x, which is just h, okay, because these guys are going to cancel out. So what do we have? Well, this is x squared plus 2xh plus h squared plus 2 minus x squared minus 2 all over h. And so again, what cancels? The x squareds cancel and the 2's cancel. So I'm left with 2xh plus h squared over h, which is h times 2x plus h over h. Those cancel out and I can just get 2x plus h. Okay, so that's your answer for part A. Okay, so we can erase this and we can write down let's write it down in black instead. It'll show up a little bit better. So this would be 2x plus h. Okay, now what we're going to do is we're actually going to grab for this next one, okay, for B, we're actually going to use the point 1 over 3 up. So it's the same exact story here. Now watch. I'm going to get rid of all this. Okay, so we'll just erase all this. It might take a second here. I suppose I probably could have just highlighted it all. But it'll give you a breather, right? Okay, so let me again draw out the picture of what's going on here. It appears that we're still using this function x squared plus 2. So I'm going to draw that guy out. So this is f of x, which equals x squared plus 2. Now, we just did it out with just those numbers, or these letters up here. I'll actually use some numbers. So let's say we go 1 over. Well, when we go 1 over, okay, when I go 1 over, it's not drawn perfectly, okay, but if you plug in 1 into this, f at 1 is equal to 1 squared plus 2, which is 3. So the height value comes out to be 3. Okay, that's this first point right here. Now, the next point is we're going to grab some other point out there, which we're going to just call x, and it's going to have a certain height value. Now, here's the thing. We're going to let x equal 1.3. So we're going to call this guy 1.3. So let's talk about the height value here. Well, the height, I should probably not have these on the axis because it might be confusing for you. Of course, I just erased the whole axis, so that's not as... Okay, there we go. So at 1.3, the question is, what's the height? Well, it is 1.3 squared plus 2. That's this height value here. So let me grab my calculator. I'm getting 3.69. Okay, so the height value is 3.69. So this right here is the change in the y. This right here is the change in the x. So if I want to find the slope of the line containing those 2 points, I'm going to take the change in the y, which is 0.69. I'm going to divide it by the change in the x. And our change in the x here is 0.3. You could have got these same values by taking 3.69 minus 3 over 1.3 minus 1. Okay, it gets you these guys. So 0.69 divided by 0.3 gives me 2.3. So the slope of the line containing those 2 points, the slope of that pink line right there, is 2.3. That's the m value. It's not the equation of the line, right? It's just the slope. Now let's go ahead and use 1.1. So what we're going to do is we're going to get a little bit closer than 1.3. Now let me grab a different color for that. Let's do red. So now I'm going to grab 1.1, and I'm going to come up, and I'm going to come over. Notice that the height difference, they're much closer. not to one another. In fact, if we do the calculation, we'd have 1.1 squared plus 2, which I believe is 3.21, but let me just check it out in my calculator. Yeah, 3.21. Okay, it's tough to write in there, but 3.21. So now our delta y over delta x is the change in the y's, 3.21 minus 3 over 1.1 minus 1. So this is 0.21 over 0.1, which is 2.1. Okay. Now what I want you to notice is that this second slope, I'll draw another line in there. We'll do it in red this time. Grab my straight edge. It gets tight in here. It's not as easy to do on the computer. But what I want you to see is that the red line is a better approximation to the tangent line. I'm going to do that in dark blue. There's a tangent line that runs through this blue point right here. And the red line's in a better approximation for the tangent line than the purple line was. So the slope of the blue line, the actual tangent line, is closer to 2.1 than it is to 2.3. So what we've just done is we've gotten a better approximation for the slope of the tangent line by moving closer to this value right here. Notice that they can't be the same value, but we're moving them closer. So now I'm going to use 1.002. It's going to get real tight in here, so I'm just going to redraw it over here. So again, oops, that's not where I wanted that. So again, here is the value 1, and I'll do it in orange. Here's the value 1.002. And so they each have corresponding heights. If I plug 1 into this function right here, I get a height of 3 out. And if I plug in 1.002, I get 3.004. Okay, so what is the change in the y value? Well, the change in the y value is this length right here, which is 0.004004, and the change in the x value is 0.002, right? It's this length right here. And so if I take that number divided by 0.002, I'm going to get 2.002. So the slope of the line running through these to the m value, the slope is 2.002. Now here's what I want you to notice. The blue line is best approximated, its slope is best approximated by this last secant line, because the 0.1 and 1.002 are closer to each other than these earlier ones. Okay, so that's how we go ahead and we do those calculations. So it says for C, using the information you obtain from part B, if x becomes extremely close to the value 1, so if this guy gets really, really close to 1, what would you estimate for the slope? Well, it looks like we went from 2.3 to 2.1 to 2.002. So our best guess for the slope of the tangent line is m equals 2, because it looks like we're getting better and better approximations. We're getting closer and closer to the value 2.